squared plus 3x plus 15 is a factor of 2x to the power 4 plus mx squared plus 30n, where m and n are integers. We are tasked to find the value of m times n. So given that x squared plus 3x plus 15 is a factor of 2x to the power 4 plus mx squared plus 30n, then we can write the equation as such: x squared plus 3x plus 15 times ax squared plus bx plus c is equal to 2x to the power 4 plus mx squared plus 30n, where a, b, and c are to be solved later. So by expanding the left hand side, we can get this, and by comparing coefficients, if you look at the coefficient of x to the power 4, you can see that a clearly equals 2, and because there's no x cubed term on the right hand side, we know that b plus 3a is equal to 0, so we can solve b equals -6. We also see that there's no x term on the right hand side, so the coefficient of x, which is 3c plus 15b, is also equal to 0, and hence we solve that c is equal to 30. By looking at the coefficient of x squared term and the constant term, we can solve n is equal to c over 2, which is 15, and m is equals to c plus 3b plus 15a is equals to 42. Now that we have both m and n, we can find that mn is equals to 42 times 15, which is 630. Different real numbers x, where 0 degrees is smaller or equals to x is smaller or equals to 360 degrees. Satisfy the equation 3 sine x minus 4 sine cubed x equals half. The equation given is 3 sine x minus 4 sine cubed x equals half, and we can use the identity 3 sine x minus 4 sine cubed x equals sine 3x. And so the equation will simply become sine 3x equals half. And we can try to solve for 3x here. And solving 3x, we will get 3x equals 30 degrees plus 360 degrees k, or 3x equals 150 degrees plus 360 degrees k. And hence, dividing everything by 3 on both sides, we can see that x equals 10 degrees plus 120 degrees k, or x is equals to 50 degrees plus 120 degrees k. And by subbing in a few values of k, we can find 6 values of x, where x is between 0 degrees and 360 degrees. And therefore, we get that the answer is there are 6 solutions in total. The equation 1 minus sine 2a over 1 plus cosine 2a is equals to tangent a minus 1, which is now equals to 0. And we're tasked to find tangent square a. How do we approach this question? Let us try to simplify the left-hand side first. And we know the double angle identities for sine and cosine are sine 2a equals 2 sine a cosine a, and cosine 2a is equals to 2 cosine square a minus 1. By using them carefully, we can slowly manipulate the left-hand side to become sine a minus cosine a squared over 2 cosine square a. And by dividing cosine squared on both the denominator and the numerator, we can express this as tangent a minus 1 squared entire thing over 2. This is helpful because everything else in the question will be involved with tangent a. So by making everything in terms of tangent a, the question is easier to solve. So we simply get that tangent a minus 1 squared over 2 is equals to tangent a minus 1. And if you notice that this is actually just a polynomial, and we can see that the roots will be tangent a minus 1 equals 0, or tangent a minus 1 is equals to 2. And since the question stated that tangent a minus 1 is not equal to 0, we can deduce that tangent A minus 1 must be equals to 2 for this to be satisfied, and therefore tangent A must be equals to 3, and we find that tangent square A is equals to 9. Given the equation sine pi over 4 minus x is equals to 3 over 5, where x is between 0 and pi over 4, and we're supposed to find 15 cosine 2x over cosine pi over 4 plus x, and that seems to be a pretty complicated fraction. So let us just gather what we have first. By the Pythagorean identity, we can deduce that cosine pi over 4 minus x is equals to 4 over 5, because sine pi over 4 minus x is equal to 3 over 5 as given in the question. We can also realize that we can conveniently find cosine pi over 4 plus x, which is equals to cosine 90 degrees minus pi over 4 minus x. So that is really just sine pi over 4 minus x as given in the question, which is equals to 3 over 5. And now we need to find cosine 2x. And how do we find cosine 2x? We can rewrite cosine 2x as sine pi over 2 minus 2x, and that will be sine 2 times pi over 4 minus x, and by applying the double angle formula for sine, we can get that it as 2 sine pi over 4 minus x times cosine pi over 4 minus x. And since we know both of these values, we know that this is just 2 times 3 over 5 times 4 over 5, and hence 15 cosine 2x over cosine pi over 4 minus x is simply just 15 times 2 times 3 over 5 times 4 over 5, and the entire thing over 3 over 5. And the 3 over 5 cancels out. So the answer is just 15 times 2 times 4 over 5, which gives us 24. Question. We need to find the coefficient of x cubed in the expansion of 1 plus 2x plus 3x squared plus 4x cubed, the entire thing to the raised to the power of 8. To find the coefficient of x cubed, we look for all possible ways to select terms from the expansion that will result in x cubed. We will use the multinomial theorem here. To obtain x cubed, we need to consider the following combination of terms from the expansion. For the first case, this is when we select 3 2x terms. Each 2x will contribute x, and we need 3 of them to make x cubed. The number of ways to choose 3 terms from 8 is given by 8 choose 3, and the contribution of coefficient from each 2x is 2. So the total contribution from 3 2x terms would be just 8 choose 3 times 2 to the power of 3, which is equals to 448. For the second case, it will be we only have 1 for x cubed, and this term will directly contribute to x cubed, and the number of ways to choose one term from 8 is just 8, and the contribution of coefficient from 4x cubed is just 4, and so the total contribution to the coefficient of x cubed in this case will be 8 times 4, which is 32. For the last case, it is if we choose one 3x squared term and one 2x term. The 3x squared and contributes 1x squared, and the 2x contributes 1x, so together they will make the x cubed. And the number of ways to choose one 3x squared term from 8 is 8 choose 1, and the number of ways to choose one 2x term from the remaining 7 terms is 7 choose 1. And the contribution to the coefficient from x squared, 3x squared is 3, and the contribution to the coefficient from 2x is 2, and therefore the total contribution to the coefficient of x cubed in this case would be 7 times A times 3 times 2, which is equals to 336. Now, by adding these three numbers up, we find the total contribution is equals to 448 plus 32 plus 336, which is equals to 816. We are to find the maximum value of 1 plus x minus 99x squared over x times x squared plus 1, where x is between 1 over 100 and 1 over 10. So we can actually notice that the function is decreasing from x from 1 over 100 to 1 over 10. You can work this out by drawing the graph of the denominator and the numerator, or you can complete the square to see this. Therefore, we can simply evaluate the function at x equals to 1 over 100, which simplifies to 100. 4 points OPQR have coordinates 0, 0, 0, 30, x, y, and 20, 0, respectively, where the point Q's lies on the curve y equals 50 minus x squared in the first quadrant. Let omega be the polygon OPQR with four sides OP, PQ, QR, and RO. What is the maximum possible area of omega if this area must be an integer? So we know that the three of the coordinates are fixed, and the last coordinate will be x and 50 minus x squared. And with this, we can apply the shoelace formula to write the area as a very nice quadratic. And by maximizing the quadratic, we'll get that the area equals 505.625, and therefore the maximum possible integer area would be 505. Girls and 5 boys in a junior class, and 4 girls and 9 boys in a senior class. A committee of 7 members is to be formed by selecting students from these two classes. Find the number of ways this can be done if the committee must have exactly 4 senior and exactly 5 boys. To solve this problem, we can break it down into 3 different cases. Case 1 would be if we are selecting 2 senior boys. In this case, since we select 2 senior boys, we know that we will select 2 senior girls and 3 junior boys. And the number of ways to select 2 senior boys will be 9 choose 2. The number of ways to select 2 senior girls will be 4 choose 2. And the number of ways to select 3 junior boys will be 5 choose 3. So the total number will be 36 times 6 times 10, which is 2160. Now, if we consider the case 2, where we choose 3 senior boys in total, we will have 3 senior boys, 1 senior girl, and 2 junior boys. So the number of ways to choose the senior boys will be 9 choose 3. The number of ways to choose the 1 senior girl will be 4 choose 1. And the number of ways to choose 2 junior boys will be 5 choose 2. And lastly, the number of ways to choose 1 junior girl from the 5 girls will be 5 choose 1. And so the total number of ways would be 84 times 4 times 10 times 5, which is 16,800. And for case 3, if we choose 4 senior boys in total, we will have 0 senior girls and 1 junior boy and 2 junior girls. So the number of ways to choose the 4 senior boys will be 9 choose 4. And the number of ways to choose 1 junior boy will be 5 choose 1. And the number of ways to choose 2 junior girls will be 5 choose 2. So the total number of ways for case 3 will be 126 times 5 times 10, which is 6,300. So if we add these 3 numbers together, we get 2160 plus 16,800 plus 6,300, which gives us 25,260 as our final answer. Suppose x is a real number. Find the largest possible integer that can be attained by the expression 7,770 minus the absolute value of x minus 10 over the absolute value of x minus 5 plus the absolute value of x minus 15. So we want to maximize the numerator, which is 7,770 minus the absolute value of x minus 10, and this will happen at x equals 10. And we also want to minimize the absolute value of x minus 5 plus the absolute value of x minus 15. And we can see that this will happen between 5 and 15. So obviously, if you want to maximize the numerator and minimize the denominator, we just pick the value of x at 10. So therefore, we just substitute x equals 10 in, and the expression will simplify to 7,770 over 10, which is just 777.